Okay, so now we want to talk about what these activation functions are. So we can have different kinds of activation functions. Remember, we're going to send this stuff, which is just the inputs multiplied by something, into here. And now you should note that this, although this is all matrix and vectors and stuff, but the actual result here, which is the same thing as what this is just a number, right? This is a number. These are numbers. When you sum them all up, you get a number. So what we're going to get into this node is a number. So we can talk about what we do with that number. So if the number is 2, we could send it to -2. If the number is -1, we could send it to, Anyway, so this, well, here, if we do it like what we have here, this is called a linear activation function. And it's also just the function that takes the A and gives A out. That's very linear. And it's not very interesting. And it also doesn't satisfy a requirement that it's between -1 and 1. Which actually, in this case, looks like, well, anyway, it's not between -1 and 1. But anyway, we could do this kind of activation function. That would be called a linear activation function. Okay, so the next one is maybe some shape like this. So first of all, you can see that it starts at 0, or it's bounded by 0 and 1. By the way, I made a mistake. It doesn't have to be bounded. Well, okay, so it's bounded between 0 and 1. So this has a nonlinear shape. And so what it does is we can say that it squashes the neuron's pre-activation to between 0 and 1. So the pre-activation can be any number like -3 up to +3 or any other numbers. The pre-activation can be anything, but the output, even if this was way down here at -100 or way up here at +100, the output will always be between 0 and 1. So we can say that it squashes the pre-activation to something between 0 and 1, or the output is between 0 and 1. It also is always positive since it's between 0 and 1. It's bounded because it's bounded by 1. It never gets bigger than 1. And it's also strictly increasing. So these are some of the properties of this curve. Now this particular curve comes from this expression here, which this is just 1 over 1 plus e to the minus a. Sometimes it's written as SIGM of a, but this is what it is. You can call it anything you want, but this is what it is. 1 over 1 plus e to the minus a. This is called, this particular function is called the sigmoid curve, or also called the logistic function. This is its definition. And it has this property, like we said, of squashing everything to between 0 and 1. So very large changes in this direction don't result in much change in the height. And that can be an important or useful property. So even if I move way to the right, I only get an incremental, very small change in the height, right? In fact, all the way from -infinity to +infinity, I only go from 0 to 1 in terms of change in the height. So that can be an important property. Now, one other thing is that you can see that changes from here, say -1 to +1, -1 to +1, they result in some kind of substantial change, right? -1, the height is here, and +1, the height is here, so it's changed by, say, something, maybe a half or something like that. But over here, if I change from like 100 to 500, the change in the height is only going to be minuscule. Okay, so right in this section, changes in the x direction result in some kind of substantial change in the y height. But otherwise, way over here, way down here, no. Changes in the, even huge changes in the x direction don't result in much change in the height or the y direction. nevertheless, you still should agree that it's strictly increasing. So just to reiterate, A, remember, is the pre-activation input. It's this, it's this, it's this, it's what's going inside, and then we're taking that and we're putting that into this sigmoid function, which means we're putting it in here. Now, you should be clear that this is never negative. Even though there's a negative sign here, that's negative in the exponent of the e. This is e to the minus a. That doesn't make it negative, right? You should check that, make sure you know that. So, so it's always positive. So like we said, it's always positive, and it's never greater than 1. You can figure that out or study that or find some video that explains that. But I think you can see it from the fact that basically it means that the denominator is never bigger than the numerator. Right, the denominator is always bigger than the numerator. So it's always less than 1. Okay, and it's bounded means bounded from above, and also it actually is bounded from below. Okay, the next one we're going to look at is a different one, which looks like this. It seems to look pretty similar, but notice that it is bounded from above by 1, but it's bounded from below by -1, so it's not the same function. And this is called the hyperbolic tangent, which is actually the inverse of the tangent function, which you probably know. Tangent function. This is the tangent tan h function called the hyperbolic tangent function. And it's defined as this. Now, I hope you know that this means e to the a, and this means e to the minus a, this means e to the minus a, this means e to the a. So here's a minus, here's a plus. So remember, a is the input, a is what's going into the neuron, and then we're going to do this hyperbolic tangent of whatever we're getting as the input, and that's going to be the output. So we're doing this to a, which means we're doing this to a, which can also apparently be written like this. And okay, so let's notice what about this. It still squashes it, but this time between -1 and 1. It can be negative, it can be positive. It is still bounded from below and bounded from above, and it still is strictly increasing. Okay, so this is similar to the this one, to the sigmoid function. That's not the same. And this one is the hyperbolic tangent. I'm not sure. Maybe just to check this out, does this work? I just looked up graphing calculator online. I wonder if we can get graphs of these things. Maybe not. Do they have e to the x or anything like that here? They don't have it. Functions. Oh, okay. Arctan. Hyperbolic tangent. Sorry. It's different than the arctan. Okay. Hyperbolic tangent. Let's see how we do this. Not sure how to work this. Oh. 5. I'm not sure how we do this. Well, you can try and figure it out, but hopefully it shows you how it shows you a graph of this. I don't know what to input in here, but it shows you a graph so that it would look like what we just saw, like something like this. Okay, so that's called the hyperbolic tangent function. So the arctan, by the way, and the tan h are kind of the same functions. At least for real numbers, they are the same. Okay. Anyway, there's one more, and that's this one, this shape. And this is kind of similar to the linear one. Well, at least this part from here on is similar to the linear one that we saw before. Remember, the linear one looked like this. And if we just start from here, it's the same thing. Starting from here, it's the same. You can see that here, right? At 0, it's 0. At 1, it's 1. At 2, it's 2. And so for this part over here, it's the same. But left of 0, it's just defined to be 0. So it's not the same as the linear one, so it's not called the linear one. So it is called the rectilinear function, or the rectified linear activation function. And another way to describe it is with this. It's just the maximum of 0 or A. What does that mean? So A is the input. Remember, A is the input. So here, if A is -2, we would put a -2 here. So which is bigger, 0 or -2? So 0 is, so we would choose 0 for the output. So at -2, we'd get 0. How about at -1? If I put a -1 for A, what do I get? I have to choose between 0 and -1, which is bigger? 0, so the output is 0 still. So whenever A is negative, 0 is bigger than that, so the output is 0, so it looks like this. As soon as A starts to become positive, for example, here A is 1, which is bigger, 1 or 0? 1 is bigger, so the output is the bigger of the two, the larger of the two, so it's 1, so the output is 1. So we get this shape. So we can use the max function. It's also called the rectilinear function. In our case, we're using it as an activation function, so we'll call it the rectilinear activation function. Okay, this one is also bounded by 0. I should say, sorry, bounded from below by 0. It's not bounded up from above. It can get as large as we want. There's no upper bound. It is strictly increasing. Strictly increasing means it's never the same. But anyway, okay. Basically, it's increasing. Basically, it never decreases. Okay, I'm not sure if we call it strictly increasing, but it never decreases. And then they also say that it tends to give neurons with sparse activities. What does that mean? That means, going back to this picture, remember we're talking about we have a bunch of inputs and some weights, and we multiply the weights times the inputs to get the pre-activation, or what gets sent into this neuron. But when we then we're going to pass that through an activation function, and we looked at a couple different possible activation functions. But this last activation function, this one here, a lot of times we're just going to get 0, right? Because whenever the input is negative, we're just going to get 0 every time. Whereas here, when the input is negative, we're not going to get 0. We're going to get like some negative numbers as the output. But here, whenever the input is negative, the output is going to be exactly 0. So when a neuron outputs nothing, we say it's really not active, right? So we're going to get this neuron is going to be not active a lot of the time. And if we're going to later be looking at pictures with many neurons, so a lot of them will be not active a lot of the time. So that means sparse activity. Okay? A lot of neurons are not active, or one neuron is not active often. It means sparse activity. So these are the 4 different popular choices for the activation function. So this one,